Hello. In the previous lecture, we were discussing comparison test. Today, we are going to continue the same discussion and let us see some new problems over comparison tests. Okay. So, so we have already seen that if an and bn are positive term series, then and an is less than equal to bn, then summation bn convergent implies summation an convergence. Okay, and summation an's divergence implies summation bn's divergence. This is something that we have already done. Okay, so this is called as the comparison test. Now let us do something called as limit comparison test. And this is also quite important. And we'll see how all these things we'll use in conjunction of one another. Now, what is limit comparison test? See, I'll be just giving it a little bit of insight. I'll not derive it or prove it. See, if an and bn are greater than 0, even eventually also, like if for some finite number of terms they are not, then eventually if they are positive, then suppose an upon bn converge towards L of L, okay? And if L belongs to R and L is greater than 0, then both summation an and summation bn converge or diverge together. Converge or diverge together. Okay, see how just a little bit of understanding. I know that if an upon bn converges to L, it implies what? It implies that an upon bn can be written in between L minus epsilon to L plus epsilon for all n greater than equals to n naught. Now, since I know that an is less than L plus epsilon bn, then if summation bn converges, it implies summation an converges. Also, I know that if I would let it be this way. And now here, if summation an converges, then summation bn converges. Okay, this can also be seen from comparison test. Also, one can see that if an is less than L plus epsilon bn, then if summation an diverges, then it implies summation bn diverges. And the same thing from here, if bn is like L minus epsilon less than an, if summation bn diverges, then summation an diverges. So remember that if an upon bn, if this limit comes to be a finite non-zero limit, then summation bn and summation an converge and diverge together. Two more important cases that you can think of are these, that if L belongs to R and L is equal to 0, then summation bn converges, then summation an converges. See how? I know that if the limit L is 0, if limit L is 0, whose limit L? Right, an upon bn limit is, sorry, an upon bn limit is 0. It implies what? An upon bn can be written less than epsilon for all n greater than equals to some n naught. Okay, it implies that an should be less than epsilon times bn. If summation bn converges, then summation an converges. I hope it is clear. That is, if limit L is 0, then only convergence of Bn would imply its convergence of An. And last case, third case, if limit An upon Bn goes towards plus infinity, okay, if it diverges to infinity, it implies what? It implies An upon Bn can be made greater than M for all n greater than equals to N naught belongs to natural. It implies what? It implies that M times Bn will be less than An. Now here, summation Bn, if it is divergent, then summation An would be divergent. I hope it is clear till now. So this is called as the limit comparison test. So please remember the cases. Case number one is that if limit L is finite, non-zero, then An upon Bn, like An upon Bn's limit is L, and if it is finite, non-zero, then summation An and summation Bn converge and diverge together. If this limit L comes out to be equal to zero, then summation Bn's convergence implies summation An's convergence, and if limit An upon Bn is infinite, then summation Bn's divergence implies summation An's divergence. I hope it is quite clear. Okay. Further, there are two more tests that one needs to use. One is called as the ratio test. One test is called as the ratio test, which implies what? Which implies that if summation An is a series such that An is non-zero, then if we compare this, like limit An plus 1 upon An, if we see this, and it turns out that it is equals to L, and if L is less than 1, then it implies that summation An converges. If L is greater than 1, then summation An diverges. If L is equal to 1, then this test becomes inconclusive. That is, we do not know whether it converges or diverges. I'll not say that if L is equal to 1, it becomes divergent. No. If L is equal to 1, then the test is inconclusive. That is, we need extra some conditions, or we'll have to use some different other strategy in order to prove the convergence and divergence of the series for that case. Now let us take another test that is called as a ratio test, and this is called as the root test. So sorry, root test. Now root test does what? Now if if I want to see whether my summation An converges or not, what I'll do, I'll just take the limit n tends to infinity modulus of An raised to power 1 upon. I'll do this. And if this limit turns out to be L and L is less than 1, then it is convergent. If L is greater than 1, then it is divergent. And if L is equal to 1, then it is inconclusive. Again, the same thing. I don't know what it will be. I don't know whether it is divergent or convergent. I need some additional hints in order to prove its convergence as well as divergence. I hope it is clear. So all these tests are to be used in conjunction to one another, because only then you will be able to arrive at right results. So let us start with questions, or let us start with some series, so that we'll be able to understand the applicability of these tests. So we'll be able to understand the applicability of all these tests. Okay. So already we have done some, but let us start with a few more. So I'm giving you a simple question, and that is that will give you a good amount of insight. Summation n equals to 1 to infinite a raised to power ln n is convergent, and here a is greater than 0 for a. So for what values of a? So for what values of a do you expect a raised to power ln n to be convergent? See how to do this question. As you remember, I've told you, just keep a few things in mind. I have already taught you that n is summation n equals to 1 to infinity 1 upon n की power p is a convergent series for all p greater than 1. And I know that if I can write ln, I can write this way, ln a. This is a property that is log a raised to power log x to the base a is simply x if x is greater than 0. This is something that we know. And this is by definition itself, okay? Because log and exponential functions are inverse of each other. So basically, this is a composition of function with its inverse. So instead of writing this, now I'll do this. I know that a raised to power ln n is equal to n ln a. So what I'll do, I'll write it, I write this way. A raised to power minus ln a. Sorry, a raised to power minus ln n. Okay, and this would imply 1 upon n raised to power minus ln a. I know this would be convergent only if minus ln a is greater than 1. Okay, and which would imply ln a should be less than minus 1. And I already know since it is greater than 0, so a is greater than 0, that is fine. It implies what? A should be less than, strictly less than 1 upon e. It implies that this series given to us, that is a raised to power ln n, is convergent for all a less than 1 upon e and greater than 0. These are the values of a for which this series summation a raised to power ln n is convergent. Okay, this is point number 1. Now, just think about this. If summation an is absolutely convergent, I've already given you this in hints. I've already taught you this particular thing, but still, if summation an is absolutely convergent, then summation, I'm giving you some summation m equals to n infinity am. This converges to 0 as n tends to infinity. What do you think this statement would be? C. Understand my point. If summation an is absolutely convergent, if summation an is absolutely convergent, it implies what? It implies that summation an mod is convergent. Let us take its sequence of partial sum as sigma n. Let us take summation an's partial sum as simply Sn. So if summation n is convergent, summation modulus of n is convergent, then summation n is convergent. I know this. So I can say that if summation modulus an is convergent, that is, if series is absolutely convergent, then it necessarily implies that summation an is convergent. And if summation an is convergent, that it implies that its sequence of partial sum, that is Sn, is also convergent. Now, if Sn is convergent, then what will I do? I will simply write that Sk is a Cauchy sequence, or Sn is a Cauchy sequence. Okay, Sn or Sk is a Cauchy sequence. So I'll simply write Sn or Sk would be a Cauchy sequence. What does it imply? It implies that Sk minus 1 minus Sn minus 1 modulus can be made less than epsilon for all k minus 1 greater than n minus 1 greater than some natural number. So otherwise I can write, why I have taken n minus 1, because here you don't have n plus 1. So basically, in order to preserve some sort of this particular question structure. Now remember this, here is k minus 1 and here is n minus 1. So if here you will get n, here you will get n plus 1 dash dash dash, here you will get simply k minus 2, so on and so forth. So basically what we will get from here? From here it's clear that Sn is what? Sk minus 1 would be what? A1 plus A2 dash 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 A3, sorry, A3 dash 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 An minus 1 plus An plus An plus 1 dash 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 Ak minus 1 minus Sn minus 1. So Sn minus 1 cancels this. So now this whole mod is less than epsilon for all k greater than n naught belongs to natural. What does it imply? It implies that an plus 1 dash 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 ak minus 1 mod can be made less than epsilon for all k greater than n naught belongs to natural. And from here it is quite evident that this is nothing but it is equal to summation m equals to n to, if I as n tends to infinity, I'll say that as n tends to infinity. So basically, what does it imply? It implies that m rise, sorry, this I'm going to write this way. So m goes from n to k minus 1. This minus 0 mod can be made less than epsilon, right? This is how it is. This is how it is. Now, as k tends to infinity also, even if as k tends to infinity, even if you take it as large as possible, then this particular modulus, it can be made less than epsilon. It implies what? It implies limit k tends to infinity, summation m equals to n to k minus 1, an is equal to 0 clearly. If you remember that if xn's limit is L, then xn minus L can be made less than epsilon for all n greater than n naught. So here, if I take even as k tends to infinity, this will remain intact. It will go on. This modulus can always be made less than epsilon from the given conditions. And now I know already that this mod minus 0 can be made less than epsilon. It implies that if I take a limit here, this limit, this sequence's limit is going to go towards 0, right? If you remember this, that xn minus L mod, if it can be made less than epsilon, then it implies what? Limit xn is equal to what? L. It implies what? From here, it's quite evident that limit k tends to infinity, summation m equals to n to k minus 1. K minus 1, an would be equals to what? This limit should be equal to 0. Or in other words, I can say that summation m equals to n to infinite, an would converge towards 0. Would converge towards 0. Would converge towards 0. I hope it is clear. Okay, this is one thing. Now let us move to another thing. This is something that I've already proven before also. I've just proven it now. So always remember, whenever a series is absolutely convergent, then series is convergent, then the tail of the sequence, the limit of the tail of the sequence is always 0. The limit of the tail of the sequence is always 0. Now second, just think about this. What can be said about this? Summation n equals to 1 to infinity, an sine n. Is it convergent? Is it divergent? So already it has been given to us that summation an is absolutely convergent. If it is convergent absolutely, it implies summation an ka mod is convergent, right? Or what I'll do, I'll take a modulus here. So modulus of an sine an would be less than equal to modulus of an. Since this is convergent, implies this is absolutely convergent. It implies summation modulus of an sine an is convergent. And it being modulus, it being absolutely convergent implies that summation an into sine an is convergent. Important. Okay. Now you see third example in this entire series. What can be said about this summation e raised to power n? So I told you that if summation an is absolutely convergent, then summation an is convergent. And if summation an is convergent, that implies that limit an must be 0. If it limit an is 0, then limit e ki power an would be 1, and it is not equal to 0. Clearly, summation e ki power an is divergent. Okay. Now let us move to the fourth example. What can it be said about this? Summation an square. Is it convergent, divergent? Okay. So clearly it is convergent. Why? Because I already know that summation an is convergent. If summation an is convergent, it implies that limit an must be equal to 0. It implies what? It implies an minus 0 mod can be made less than 1 for all n greater than equals to n not belongs to natural. And if an is less than 1, then an modulus would be less than an square. Always remember, because if an is less than 1, then more higher powers you take, the lesser the number would be. So an mod will be greater than an square. Since an mod is given to be convergent, it implies summation an square is convergent by comparison test. So I hope I have been able to make some justice with this kind of problem. So okay, just give me an idea of this. What do you think about this thing? Now just let me show the question to you. Okay, a little bit I'll change the question. Now see, if summation an converges, then what can be said about the following? Okay, about the following. So one thing I'm giving to you, that if an is less than 1 upon n, then it necessarily implies that summation an converges. True or false? What do you think the answer should be? So if an is less than 1 by n, then it necessarily implies that summation an converges. True or false? I'm giving you a minute to think about it, and then I'll do the question for you. Okay, so just think about it. Just think about this. See, consider an to be equals to 1 upon 2n. Clearly, 1 upon 2n is less than 1 upon n, but summation 1 upon 2n is equals to summation 1 upon 2. You can take outside, it is summation 1 upon n. And I have already proven that summation 1 upon n is divergent. It implies this is divergent. So therefore, this statement is false. That is, if an is less than 1 by n, it not necessarily implies that summation an would be convergent. Here is an example, counterexample to assert my case. What do you think about this? That if summation an converges, then then summation minus 1 raised to power n, an also converges. What do you think answer should be? True or false? Now see, if I want to prove its convergence, what I can do, I know that summation n is convergent. So I know that summation n is convergent. Then let us say that uh, this is my whatever, like, so I'll do one thing. I'll take an absolute of it. Okay, I'll take an absolute of it. So in any case, having taken an absolute, I know that this would be less than or equal to summation a. Or in other words, see, what I can do is, if I take an absolute of it, what does it imply? It simply implies that summation minus 1 raised to power n, an, instead of that, I'm considering this. So I'm going for an absolute convergence. It implies what? It implies, and here an is greater than 0. It implies what? It implies an modulus, and it is nothing but it is equals to summation an. And I know that this converges. If this converges, then it implies that summation minus 1 raised to power n, an is absolutely convergent. And always remember, if the series is absolutely convergent, then it is convergent. Okay, if the series is absolutely convergent, then series is convergent. Why? Because see, if I'm saying that a series is absolutely convergent, it implies what? It implies what? It implies that its modulus is convergent. And from comparison test, I know that an can always be written less than equal to modulus of a. So if the series is absolutely convergent, then the series is convergent. Okay, now just think about this statement. Is that true or false? If summation an does not converge, then summation n into 10 an cannot converge. Is that true or false? So certainly it is false. Why? Take an to be equals to something like, let's say pi. Okay, I know that summation pi is divergent because summation pi would be adding pi n times and limit n tends to infinity. So it will be divergent. But what is 10 pi? 10 pi is simply 0. So basically it is equals to summation 0, and indeed it is 0. So it is convergent here. So therefore the statement is false. So all these kind of things you should remember, because after all, at times questions may not be as difficult, but these are the small things that may be asked to you. What do you think now about this question? For what values of m and p does the series summation n equals to 1 to infinity 1 upon n raised to power m 1 plus 1 upon n raised to power p is convergent? Okay, so for what values of m and p does this particular series converge? So see, understand one point, that n raised to power m plus n raised to power m minus p would be certainly greater than n raised to power m. And it implies that 1 upon n raised to power m plus n raised to power m plus p would certainly be less than 1 upon n ki power m. Now, if m is greater than 1, if n is greater than 1, then summation 1 upon n raised to power m is convergent, and which implies that summation 1 upon n की power m 1 plus 1 upon n की power p is convergent. So here it does not depend upon p, but it depends upon m. So the condition is that m should be greater than 1 and p may belongs to any real number. Now, what if m is lying between 0 and 1? What if, I'm just giving you a question. Think about this. What if m lies between 0 and 1 and p is greater than 0? Let us take it for simplicity that p is greater than 0. However, we've proven that it does not depend upon p. The convergence of this particular series does not depend upon p. It only depends upon 1 upon n की power m's convergence, which implies that m should be greater than 1. What do you think about this? So clearly, one can assert the case that n की power m is certainly less than equal to n. See, if m is less than n, just take n on both ends. N is obviously greater than 1. So n raised to power m would be less than n. And we know that n raised to power 1 upon n raised to power p would be less than equal to 1 because I know that n raised to power p would be certainly greater than 0. So I can say that 1 upon n raised to power p would be certainly less than 1. And it will give you that n raised to power m plus n raised to power m upon n raised to power p is certainly less than n raised to power m 1 plus 1 upon n raised to power p. And from here, it's quite conclusive that that n raised to power m plus n raised to power m upon n raised to power p is certainly less than 2 times n raised to power. Sorry, n raised to power m is less than n, right? So this is less than n, and this is 1 plus 1 because 1 upon n की power p is less than 1 and n की power m is less than n. So clearly, I can state that 1 upon 2n is greater than, or you can say that, sorry, 1 upon, what should I do? So it is, I'll say that 1 upon 2n is less than, is less than, because this is 2n, right? So if I do 1 upon 2n, so 1 upon 2n is less than 1 upon n की power m 1 plus 1 upon n की power p. Now, since this is divergent, since 1 upon 2 is divergent, it implies what? That this series also divergent. For what? For all m less than equal to 1, greater than 0, and p greater than 0, this series is divergent. I hope it is quite clear to you. Okay, now let us do some questions based on comparison tests and all those stuff that we've been doing till now. So let us do a few more questions so that your understanding becomes a little bit firm in this particular topic. Now let an be greater than equal to 0 for all n belongs to natural. Now if summation an converges, then summation an square converges. True or false? I hope I have done it for you. It is true. Why? Because again, if summation an converges, then it implies that limit an would be 0. And if limit an is 0, that implies an minus 0 what can be made less than 1. And for that matter, an modulus would be greater than an square. And clearly, its convergence implies its convergence. Since an is greater than equal to 0, whether you write mod or whether you don't write mod, it is one and the same thing. So convergence, this is convergent, therefore it implies that summation an square is convergent. Is converse true? Just think about it. If is converse true? Is converse true? Certainly not. Why certainly not? See, take an to be equals to 1 upon n. I do understand that summation an square is convergent. Why? Because I know that since summation 1 upon n square is convergent. But it's convergent does not implies that summation 1 upon n is convergent. So if summation an square is convergent, it does not imply that summation an is convergent. Now let us take another example. What can be said about this? Again, the same. If an is greater than equal to 0 and summation an is convergent, then does it imply summation root over an into an plus 1 is convergent? Does it imply that summation root over an into an plus 1 is convergent? See, indeed it is. Understand, always whenever such things come, you know that an is positive, this thing is something like geometric series. So what I'll do, consider an and an plus 1 both are greater than 0. Consider its arithmetic mean, and I know that arithmetic mean is always greater than equal to geometric mean. So what does it imply? It implies that an plus 1 upon 2 is always greater than equal to root over an into an plus 1. Or in other words, other way I can just write this thing as root over an into an plus 1 is less than equal to an plus 1 upon 2. This is convergent. It hardly makes difference if I take summation from n plus 1. So this is also convergent. This is also convergent. So from comparison test, this is convergent. So I can write by comparison test, summation root over an into an plus 1 is convergent. I hope this is clear. Okay, now I'm asking you a simple question. Does the converse exist for the same statement? Just think about it. I'm giving you a minute or so. Does the converse exist? Yeah. So sorry. I hope everybody have thought about it. So what do you think that is the converse true? So answer is that indeed it is. Indeed it is true that if an is convergent, that if summation n is convergent, that it necessarily implies that summation root over an into an plus one is convergent. Now I'm asking that whether its convergence, that is summation root over an into an plus one's convergence, implies summation n convergence. So answer is no. And here I supply with you supply to you a counter example. Just remember this example. Okay. So see, uh, just think about this. So let us consider that an is equals to 1 if n is odd, and it is equals to 1 upon n raised to power 4 if n is even. If n is even. So you see that if I just try to find this thing, k equals to 1 to n root over a k into a k plus 1. So it would be simply, if I less than summation k equals to 1 to 2n. Why did I do to 2n? Because so in order that I can create pairs here. So ak into ak plus 1. See clearly, if k is even, then this is even, then this k plus 1 would be odd. If k is odd, then k plus 1 would be even. So if I am going to k equal to 1 to 2n, I will be able to prepare n pairs. And if n is odd, then it is 1. And if n is even, this is 1 upon n raised to power 4. So clearly, it would be less than summation k equals to 1 to, I should say two, sorry, I should write it once so that you'll be able to get it, and then we'll see. So consider this particular sequence. An is equal to 1 if n is odd, and it is equals to 1 upon n ki power 4 if n is even. Okay. Now, just think about this. I know that if I take a series summation k equal to 1 to n, this is the sequence of partial sum till n, and this is till 2n plus 1. So clearly this will be more. Now let us think about this, what it is going to be. So I'm writing it here somewhere so that you just don't get disrupted with this. So summation k equals to 1 to 2n root over ak into ak plus 1. It will be equals to what? It will be equals to root over a1 a2 plus root over a2 a3 plus root over a3 o4. See, if I place 1 here, so this is root over a1 a2. If I place k equal to 2, so this is a2 a3 and so on and so forth. Okay, so this is certainly equals to what? It is equals to 1 upon 2 square, because you see this is 1 upon 2 ki power 4 by 2 plus again 1 upon 2 square. So from here you get 1 upon 2 square plus 1 upon 2 square. Okay, now here it would be like plus 1 upon 4 square, and again you just think about this a4 a5, it will be 1 upon 4 square plus 1 upon 4 square. Okay, and instead here it is 2n, so I'll write 2n. So I'll write the last term here, so sorry about it. So let us fix the last term first. So at the end, what I'll get, if k is the last is 2n, just before it would be root over a2n minus 1 a2n plus root over a2n a2n plus 1. So in any case, just think about this. This will a2n 2n minus 1 is odd, so this is 1. A2n is, so it will be 1 upon 2n whole square plus 1 upon 2n whole square. So clearly this particular thing, if I take 1 upon 2 square common, so this is 1 upon 4, and this is equal to what? The first bracket will be equal to what? Just think about it. So if I take 1 upon 2 square common, this is 1. Okay, so this is, just think about it. What I want to tell is, let us say this is, okay, so I'll have to take, so this is 2, I think. Oh, okay, so sorry about it. So this is equals to 2 times 1 upon 2 square, fine. Here it is 2 times 1 upon 4 square plus 2 times 1 upon 6 square dash 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 2 times 1 upon 2n whole square. So what I'll do, I'll take 1 upon 2 square common. Right. So from here, if I take 2 square common, I think 2 also let me take common. 2 upon 2 square, if I take common, this is 1. I think this would be 1 upon 2 square. This will be 1 upon 3 square dash 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 1 upon n square. So basically, I know that this series would be this series here is simply this is equals to 1 upon 2. This is how it is. So I know if this is convergent, then this is convergent. By comparison test, I know that summation root over ak into ak plus 1 is convergent by comparison test. Now, does it imply that summation an is convergent? Indeed, it is not. See why? I know that what is an for generating this kind of pattern. What I took as an was if n is odd, 1 if n is odd, and 1 upon n ki power 4 if n is even. Now just think about it. If I take summation an, then obviously this is convergent. So the portions like this is convergent, but these portions, let me take minus. So these portions, that is the portion like these a2 and minus 1, like a2 and minus 1, this will be a1 plus a3. This is all, it is all going towards infinity because these are all ones. This it is one added infinite number of times. Overall, this is divergent. So clearly, if I supply this as a counterexample, you can clearly see that summation root over ak into ak plus 1 is convergent, but summation an is not convergent. Remember, if summation an is convergent, then summation root over an into n plus 1 is convergent by arithmetic mean greater than equal to geometric mean. But the converse is not true. However, converse can be made true. However, I'm writing it here. However, converse can be made true. Let us see how. So what is that extra condition? The extra condition is that an must be a monotonically decreasing sequence for that matter. So an must be monotonically decreasing sequence. See how. So if an is monotonically decreasing, then an must be greater than an plus 1. Fine. Then an into an plus 1 would be greater than an plus 1 whole square. And it implies what? This would be less than root over an plus 1 square. Okay. And it will imply that an plus 1 is less than root over an into an plus 1. Then the convergence of root over an into an plus 1 will definitely mean summation an's convergence. So here it implies that summation root over an into an plus 1 is convergent. Then it necessarily implies that summation an is convergent. Only when an is a monotonically decreasing sequence. Only when an is a monotonically decreasing sequence. Please do remember. Otherwise, the converse will not be true. Okay, so this is an important topic that I wanted to teach you. So please do remember all this particular question and all the variations that may be asked in the exam. Just think about this. If summation an is convergent, if summation an is convergent and an is greater than 0, then what can be said about this series? Summation an plus 4 raised to power n plus, sorry, an plus 4 raised to power n upon an plus 5 raised to power n summation n equals to 1 to infinity. What can be said about this series? Is it convergent or divergent? see, I know that summation an is convergent. I know that summation an is convergent. If summation an is convergent, then limit an should be equals to what? 0. It implies that an minus 0 mod can be made less than 1 for all n greater than equals to n naught. So I can write here that summation an plus 4 ki power n upon 5 ki power n can be written less than, or let me not write at one summation. Let me take it off and then see. So I'll write it as 1 plus, so sorry. So I can write it as an plus 4 raised to power n upon simply 5 raised to power n. I have avoided this. An is positive and it can be written less than 1 plus 4 ki power n upon 5 ki power n. Clearly 1 upon 5 ki power n is a convergent geometric series, and 4 upon 5 ki whole power n. This is also convergent geometric series. This is also convergent geometric series. It implies what? It implies by comparison test that this is convergent. Both of them are convergent series. This is convergent series because this is a geometric series with the common ratio 1 by 5. And the next one, this is also a geometric series with the common ratio 4 by 5. So both of them are convergent. Since both of them are convergent, remember that the sum of two convergent series is always convergent. So therefore, this particular series is convergent. Otherwise, what you could have done is, okay, so this is clear. Now, just try to do this. What can you say about this? What can you say about this? Summation n equals to 2 to infinity 1 upon ln whole raised to power p greater than 0. Is it convergent or divergent? Okay, so what I'll do, let us compare this with 1 upon n. See how. Limit n tends to infinity 1 upon ln n whole raised to power p divided by 1 upon n. It is equals to limit n tends to infinity n upon ln n raised to power p. Okay, so both of them are tending to infinity. So what I can do, I can use an L'Hospital rule. So I'll use an L'Hospital rule here. I'll differentiate up numerator, which is equals to 1, and I'll differentiate this. This will be p ln n whole raised to power p minus 1 times 1 upon n. So this n comes here. Or instead, what I can do, instead of doing this, what I can do, I'll use a replacement. So see, I know that. So what I'll do, I know that n is tending to infinity. So I'll assume n equals to e ki power m and m tending to infinity. This is one and the same thing, because if m tends to infinity, then e ki power m tends to infinity. And if e ki power m tends to infinity, then n tends to infinity. So instead of writing this, what I'll do, I'll simply write limit m tends to infinity. This will be e ki power m upon e ki power m log, so which is simply equals to m raised to power p. Now, if I differentiated p times above and p times below, so I'll get limit by using L'Hospital. If I differentiate m p times, so I'll differentiate p times the numerator as well as the denominator. And this will be equals to p factorial. So it is going towards plus infinity. So divergence of this particular, so here, the divergence of 1 upon n, since 1 upon n is divergent, it implies that summation 1 upon ln n raised to power p is divergent. Okay, I hope it is clear. Okay, this is from limit comparison test. So this is from limit comparison test. I've already stated the limit comparison test. Kindly see that. Now, just think about this. What can be said about this? Summation n equals to 2 to infinity sine 1 upon n upon root over n. Always remember that if theta, let's say if it lies between 0 and pi by 2, then I can always write sine theta less than theta. Okay, if theta is positive, I can simply write this. So sine 1 upon n can always be written less than 1 upon n. And from here, it is clear that 1 upon, sine n upon root n can be written less than 1 upon n की power 3 by 2. Since this is convergent, so by comparison test, this is also comparison. This is also convergent. So by comparison test, I know that summation sine of 1 upon n divided by root over n is convergent. I think there is a flaw here. Okay, this is what it is. Or otherwise, you can use a limit comparison test here also. So what I can do, I can compare it with this. So sine 1 upon n upon root n, I'm dividing this in entirety by 1 upon n की power 3 by 2. And I'm taking a limit n tending to infinity. So it implies what? It implies sine 1 upon n divided by n as n tends to infinity. So because, divided by 1 upon n. You can do it on your own. N की power 3 by 2 will go up, and root n cancels root n. So this would be n, and I'm releasing it here. So as n tends to infinity, this limit would go to 0. And certainly if it is non-zero, it implies that since summation 1 upon n की power 3 by 2 is convergent, it implies summation sine 1 upon n upon root over n is convergent. Okay, now let us take a few more examples. I know I'm going a little bit in hastiness I'm showing, but I hope all these things you can do on your own as well. But I just want to show you how to go about these questions. So let us try to do this. What can you say about this particular example? What can you say about this particular example? Is it convergent? It is divergent? What it is? So what I'll do, I'll simply use one simple limit comparison test. So important. So always remember, limit comparison test is very important. So use limit comparison test. So what I'll do, ln n upon root n, I'll divide it by 1 upon root n. And I'll take the limit n tends to infinity. This particular limit would come as infinity. And I know that since summation 1 upon root over n is convergent, then it implies that summation ln n upon root n is also convergent. It is also convergent. This is quite evident. See, why it is? Because I already stated that if the limit in limit comparison test, if you compare your given series by a given series or like this an with some bn, and if summation bn diverges, then summation an also diverges, provided limit is infinite. So since limit is infinite, then since I know that summation 1 upon root n is divergent, then this is divergent. What can be said about this? So I taught you a few more methods. So one of the method was, if you remember, it was ratio test. Okay, so root test. So according to root test, limit n tends to infinity, e raised to power minus n square, whole raised to power 1 upon n. This will go certainly to 0, and which is certainly less than 1. So clearly this is convergent by ratio test. Root test. So by root test, the series summation e raised to power minus n square is convergent. Now, if you don't want to do this way, you can do this way also. Just think about this. E raised to power x is after all what? It is 1 plus x square by 2 factorial dash dash dash. So clearly, e raised to power x is greater than x square by 2. Okay. So e raised to power minus of n square is greater than, or what I'll do, I will write this way. So sorry. So what I'll do, I'll write this way. So I'll write e raised to power n square, or I can here also write as well, or I can write that e raised to power x is greater than x. From here, see, these are all getting added. If x is greater than 0, then I can use either this or this. So it is better to use this. So e raised to power x is always greater than x. It implies that e raised to power n square is always greater than n square. And 1 upon e raised to power n square will be less than 1 upon n square. Or in other words, e raised to power minus n square is less than 1 upon n square. Since this is convergent, it implies this is convergent. Since I'll write since summation 1 upon n square is convergent, it implies what? It implies summation e raised to power minus n square is convergent. Okay, so this is quite evident. What do you think can be said about this particular series? Summation 1 upon n 1 plus 1 upon n. So I'll use again a limit comparison test, and I'll compare it with limit n tends to infinity 1 upon n into n raised to power 1 upon n, and I'll compare it with 1 upon n. It is simply 1 upon n raised to power 1 upon n. And remember, limit, if I have not proven it, I'll prove it. This limit is always equals to 1. I have proven it previously, but if you've forgotten, that this limit comes out to be 1, certainly non-zero. Now, since 1 upon n, this particular series is divergent, then it implies that summation 1 upon n raised to power 1 plus 1 upon n is divergent. Okay. Now, what can be said about this? What can be said about this series? Is it convergent or divergent? Summation n equals to 1 to infinity sine of n pi divided by n plus 1. So what I'll do, I'll compare it with something like this. So limit n tends to infinity. I'll simply try to compare it by 1 upon n. Okay, so I'll try to compare it by 1 upon n. Now see, uh, so what I'll do, I know that as n tends to infinity, so as n tends to infinity, n pi upon n plus 1, this goes towards pi. This goes towards pi. Okay, this is one thing. Now, this will be equals to what? This will be equals to n times sine of n pi upon n plus 1. Okay, now what I can do instead is, so I can write this as limit n tends to infinity sine of pi minus 1 upon n plus 1. Just think about it, if it is fine or not. So I think I should write pi. Okay, so this is pi minus pi upon, I have forgotten n here. Okay, so see, pi minus pi upon n plus 1. So this is n pi plus pi. So this, and I know that as n tends to infinity, this is a very infinitesimal small quantity. Pi minus theta is sine theta. So this is sine of pi upon n plus 1. And I know that whether I write n or whether I write n plus 1, this is one and the same thing, because as n tends to infinity, n plus 1 also would go to infinity. So instead of n, I will supply n plus 1 here, and this is sine pi upon n plus 1. Now, instead of writing this, what I'll do, limit n tends to infinity, I'll write sine pi upon n plus 1 divided by 1 upon n plus 1. So multiply pi here and multiply pi here. So clearly this limit goes towards pi. since this limit is pi and this is non-zero, and I know that since summation 1 upon n is convergent, it implies what? It implies that summation sine of n pi upon n plus 1 is convergent, is divergent. So sorry about it. Since summation 1 upon n is divergent, then summation n pi upon n plus 1 is divergent. This is from limit comparison test. Okay. Okay. Now think what can you say about this series? What can you say about this series? Summation n equals to 2 to infinity tan of 1 upon n. What can you say about this series? See, what I'll do, I'll compare it by 1 upon n. So remember, limit theta tends to 0, tan theta upon theta. This is also equals to 1. So what I can do, I will compare it by 1 upon n. So tan of 1 upon n divided by 1 upon n, limit n tends to infinity, this will come out as 1, certainly non-zero, since summation 1 upon n is divergent. So therefore, summation tan of 1 upon n is also divergent. What can be thought about this? So all these questions are quite easy. Therefore, I'm doing it in a little bit hasty manner. And I expect that even as I'm giving you a little bit of hints of doing all these questions, you can elaborate a detailed proof on your own. What can you think about this series? Is it convergent or divergent? So clearly remember that the leading term here is 1 minus cos theta. If I expand it in series, this is 1 minus theta square upon 2 factorial plus theta cube, theta ki power 4 upon 4 factorial, so on and so forth. So I can write that 1 minus cos theta can always be compared by theta square by 2 factorial. This is something that I can do. So having taken this idea, or otherwise you can convert it in the form of sine. So what I can do, I can write 1 minus cos pi by n as simply 2 times sine square theta by 2. So this is this way. And now what I'll do, I'll compare limit n tends to infinity 1 minus cos of pi upon n. I'll divide it by 1 upon n square. Now I'm going to compare with this. So it is equals to limit n tends to infinity 2 times sine square pi upon 2n. And here it is what? Here it is equals to 1 upon n square. And I'll multiply by pi square upon 4. And then I will divide it by pi square upon 4. And I'll multiply by pi square by 4. Okay. Now this limit will come out as pi square upon 2, which is certainly non-zero. I know that this is convergent, then this is convergent. It implies that summation 1 minus cos of pi upon n is convergent, since summation pi square upon 4, 1 upon n square is convergent. I know that this is convergent, then it implies that this is convergent, and if this is convergent, it implies this is convergent. I hope it is clear. Okay, now let us do a few more questions and then I'll conclude the lecture. Don't worry. Okay, just for time being, do the last question and then we'll continue the same tomorrow as well. Ln n times sine of 1 upon n square. Is it convergent or divergent? Is it convergent or divergent? So see, always remember that just I'm doing it for you. See here, limit n tends to infinity ln n upon n is always equals to 0. See why? Again, I told you on the previous day that ln's rate of growth is this. It increases at a decreasing rate. However, the rate of growth of x is simply linear and it is constant. You can take an example also. See, just for an example, if you consider a very large number, let's say 10 to the power 100, and if I take this ln 10 to the power 100 divided by 10 to the power 100, it will be equals to what? ln 10 to the power 100 would be hardly 100. And ln 10, I just forget, let's say, and this is like 10 to the power 100. So basically it is equals to 10 to the power minus of 98, which is certainly very low. It is almost tending to 0. So if you take very large quantities, large numbers, then ln n upon n, this limit will always go towards 0. You can do it using L'Hospital rule also. It's entirely up to you. So I know I can divide it by 1. I can divide it by n, sorry. I can divide it by n. And I can divide this fellow by 1 upon or what I can do, let's say, or otherwise also, let's say, here it is n square, right? So what I can do, okay, so n square is here, and I can compare it with the thing. Okay, so I can do one thing. I can compare it using 1 upon n root n by c. If I compare it, so ln n times sine of 1 upon n square divided by 1 upon n root n, which simply would be equals to what? It simply will be equals to what? So what I'll do, there is something that I can do here. So instead of this, I can write ln of n sine of 1 upon n square, and I'll do this root over n here and 1 upon n square here. Okay, so this is equal to 1 upon n root n. Fine. And so this is equal to ln upon root n times sine of 1 upon n square upon 1 upon n square, and I take limit n tends to infinity. Now clearly this is 1, and this limit goes towards what? This limit goes towards 0. You can find it on your own. So this limit goes towards 0. And I know that summation 1 upon n ki power 3 by 2 is convergent. So therefore it implies that summation ln n sine of 1 upon n square is also convergent. I told you that if limit goes to 0, then you have to see this. If this is convergent, then this is convergent. So therefore I deliberately compared it by 1 upon n root n. So that will give me a good hint. So if I compare it by n root n, 1 upon n root n, I know that this root n would be subtract. So limit n tends to ln n upon root n. This is certainly 0. See how, if you are getting confused here, see, I know that ln n is less than n divided by root n divided by root n, and I know that this is greater than 0. So by Sandwich theorem, okay, no, not by Sandwich theorem. So do one thing. You just take, I think, because by Sandwich theorem the limit is not even only tell the boundedness. So what I'll do, instead of doing this, I'll demonstrate this by using L'Hospital. So basically limit n tends to infinity ln n upon root over n. Use the L'Hospital. So 1 upon n, and this will be like 1 upon 2 n raised to power minus 1 by 2. So basically it will be equal to 2 root over n upon n, and simply it is going towards 0. So I hope you might have got a little bit of insight of how to use all these tests. I know I have gone a little bit faster. Tomorrow also I'm going to do this comparison test thing only, and then we'll see other tests as well, like Cauchy's condensation test, Cauchy's integral test, because they're also very helpful in the exam. Meanwhile, try to do as many as problems as possible on your own, and please do let me know if there is some doubt, and please feel free to give your feedback on the comment section. Till then, take care. Bye bye.